So the photoelectric effect is one of the sections in physics. It is based on the idea that light can behave like a particle. So earlier on, you will have learned that light can behave like a wave, and that was with refraction, those type of phenomenon. What we're talking about now, though, is where light behaves like a particle. So the definition for our photoelectric effect is given here. The process whereby electrons are ejected from a metal surface when light of suitable frequency is incident upon that surface. So what this is about is we know that metals have something called metallic bonding, where essentially all of the metal atoms lose their electrons and we get a sea of delocalized electrons on the surface of every metal. So remember this, where those electrons act like the glue that sort of holds the whole thing together. This is also why metals are able to conduct electricity and heat, because those electrons are free to move and act like charged carriers. At the same time, what you should also remember here is that light can be seen, or we know that light is a transfer of energy, and we can measure the energy of a single photon of light with the formula E is equal to H times F, where H is a constant that will be given to you and F is the frequency of that light. So important here that the frequency of that light refers to the number of complete waves that pass a point per second. And we remember also that when we're talking about electromagnetic radiation, we're talking about all these forms of radiation that travel at the same or at a constant speed, that being the speed of light 3 times 10 to the 8 meters per second. Now, because the speed is constant, that means that the frequency and the wavelength are inversely proportional to each other. What that means is that when the frequency of light increases, it means that its wavelength would decrease, right? And so we remember that, or we know, hopefully, that light, the light spectrum ranges from blue, technically, actually that is violet, blue light or violet light, which has a wavelength of roughly 380 nanometers, where nanometers means times 10 to the power of -9. And that means that it also has then a frequency that is roughly 6.66 times 10 to the 14 hertz. Now, it's not necessary for you to know the exact wavelength and frequency of every color of light. What is necessary is that you understand the two ends of the spectrum. So where we have blue light as the shortest wavelength and highest frequency light, and at the other end of the spectrum, we have red light that has the longest wavelength, this wavelength around 700 nanometers, again, nanometers meaning times 10 to the -9, and that then has a frequency of roughly 4.29 times 10 to the 14 hertz. So as you can see here, red light has the longest wavelength and the lowest frequency, and blue light has the shortest wavelength and the highest frequency. Both of these, using the formula that we had just now, E is equal to HF, or can be rewritten as E is equal to H times C over lambda. That just comes from us being able to use the formula C is equal to F times lambda to convert between a wavelength and a frequency, because the speed is constant. Both of these tell us that blue light is going to have the greater energy than red light. So when we're talking about light shining on a surface, what you need to keep in mind here is that blue light and things at the blue end of the spectrum typically have more energy, and red light and things at the red end of the spectrum typically have less energy. You can remember, or you don't need to, the spectrum of light, written backwards as Roy G. Biv, which basically just says that your spectrum of light ranges from violet, indigo, blue, green, yellow, orange to red. Obviously, going further this way, we go to ultraviolet light, which is even higher energy, and going off the red end of the spectrum, we go to infrared light, which has an even lower energy than red light. Right, so the first thing that we need to understand for the Doppler effect is that any light that you shine on a surface has a specific energy. It has an energy because it has a specific wavelength and frequency. Right, so that's just a reminder of what our frequency is, and the photon energy, this with the symbol E measured in joules, the amount of energy that a single photon of light has, and that is the formula E is equal to H times F, where H is Planck's constant. It is a constant, it will always be given to you, and so the only thing that you need is either F or C and lambda if you are given the wavelength instead. Right, that is the one aspect of the light that we're always going to be talking about, is we're going to be talking about its frequency, because the frequency is directly related to the energy of that light. The other aspect of light that is important for us to understand here is something called the luminous intensity. Often we just simplify that, we just call it the intensity of the light. Right? So what intensity of light refers to is essentially how many photons, that as you can obviously see is a torch, how many photons that light is giving off. Okay? So a light that is only giving off 3 photons per second is something that we would see as very dim. So to us, the way we see things, we see intensity as brightness. When a light is more intense, what it means is that light is giving off far more photons per second, and because it's giving off more photons per second, you have more of those photons striking your eyes, and we perceive it as being something brighter. Right, so please do not confuse the frequency of light, which is only the color. Right, you can get a dull red light and you can get a bright red light, but they both have exactly the same wavelength. So do not confuse the frequency with the intensity. The intensity tells you how many photons is that light source giving you. Right, so that's the basic grounding that we have before starting with the photoelectric effect, where we can now go back to our definition. As we've said, a metal surface, we talk about metal specifically because the electrons are delocalized, meaning the electrons can actually be ejected. Now the reason why these electrons don't just float off all the time is because there are still these positive atomic kernels within the metal that exert a force of attraction on the electrons that are near, meaning that those electrons are bound to those atomic kernels, but there is a certain amount of energy that can get them to leave. Right. That certain amount of energy is called the work function. So what we say is that for a specific metal, every specific metal, it has a specific work function. Work function has the symbol W0. The work function, the minimum energy that an electron needs to be emitted from the surface of a metal. So what you'll see very often when we talk about the photoelectric effect is that we'll say the work function for graphite, or the work function for sulfur, or the work function for gold is, and then they give a value. Okay, they say that because every metal has a different work function. Right, so that work function is what's telling us this is the minimum amount of energy that is needed to eject an electron. Right, so in this case I'm going to just use a random example here. I'm going to say the minimum amount of energy required, or the minimum amount of energy required here is 4 times 10 to the negative 19 joules. So the way that this would come across in a question is you are told that this specific metal, whether it's sulfur or carbon or whatever it may be, sorry, not carbon, has a work function of 4 times 10 to the 19 joules, meaning that in order to get an electron off this metal, in order to get an electron to be able to escape the force that's holding it on there, it needs exactly, or at least, 4 times 10 to the negative 19 joules. Right, so that we call the work function. Now the way that we give them, the way that we give those electrons this energy is where we start out and we say, I'm going to shine a green light on the surface. Right? So by me telling you it's a green light, you immediately sort of know, okay, green light has a wavelength that is roughly in the middle of the spectrum, 550 nanometers. You can then use the formula if you want to. C is equal to F times lambda, where C is our speed of light, which is a constant. The wavelength is 550 times 10 to the negative 9, and we can then solve for the frequency of this green light and find that it is 5.45 times 10 to the 14 hertz. Important at this point, you should start to get to know these values in the sense that in this photoelectric effect section, we typically speak about frequencies in the range of 10 to the 14 hertz. Meaning that if you ever do a calculation, you get an answer that says your frequency is something like 10 to the minus 9 hertz or 10 to the 40 hertz. It's worth going back and checking it because the visible light spectrum, as you can see, is all in the range of 10 to the 14 hertz. In much the same way, you're going to find your wavelengths are all typically in the nanometer range, 10 to the negative 9, and you can use that to check yourself again. So, by shining a green light onto this metal surface, what that says is that we are shining a light that is ejecting or sending a series of photons onto this metal. Right? It's sending those series of photons where every single photon has a certain energy. We can calculate that energy by saying the energy of this photon is equal to Planck's constant multiplied by the frequency. Planck's constant will always be given, and we can say, therefore, the photon energy here is 3.61 times 10 to the negative 19 joules. Now, what that means is that when this photon arrives at the surface, it is going to be absorbed by an electron. This electron absorbs the photon. As soon as it absorbs it, it gains energy. When it gains that energy, it gains it in the form of kinetic energy. Now, unfortunately, in this case, the electron does not have enough energy to overcome the work function of this metal. Right? We said from the start, in order to escape from this metal, you need 4 times 10 to the negative 19 joules. Now, unfortunately, in the first case, or in the case of green light, the photon energy is less than the work function. Now, because the photon energy is less than the work function, what that means is this electron is going to absorb that photon, but that just means that it's going to go bouncing around inside the metal. It's gained energy, it's kinetic energy, it bounces around. While it's bouncing around, it gives it off to the metal, and eventually it just ends up back where it started. Important here that you see that this electron does not have enough energy to escape. Right? Because the photon energy was less than the work function, this electron stays trapped on the surface of the metal. Now, a common mistake here is to think that one electron could somehow absorb 2 photons of energy. Right? Because if it could absorb 2 photons of energy, then it would have more than enough energy to escape. The reason why that cannot happen is twofold. Number one, it can't happen because as soon as the electron absorbs 1 photon, it goes bouncing around and loses that immediately. It can't wait and gather energy. The second, and this is the proof that the photoelectric effect is evidence of the particle nature of light, is that if light was a wave, exactly that would be able to happen. Each electron would be able to wait until it absorbs enough energy and then escape. But because light in this case is coming across as a series of particles, it means each electron can only get 1 photon. Right, so these are the common pitfalls here, is that you need to realize when the photon energy is less than the work function, nothing can happen. Right? So what we say here is we say that there are no electrons ejected, or there are no photoelectrons, or the photoelectric effect does not occur. All of that is just a fancy way of saying electrons do not get enough energy to escape. Right. So now what we normally say is, the follow-up question is, what would happen if I increase the intensity of this light? So I say it's green light, but now I'm going to make it bright green light. Right? And because you know that each electron can only absorb one photon, it doesn't matter how many photons are landing on the surface. Because each photon goes to a separate electron, each electron is disappointed because it didn't get enough energy, and this process just continues where these electrons keep on absorbing energy but not enough, and so again, nothing happens. So for as long as this is true, for as long as your electron energy, so your photon energy, is less than your work function, nothing happens. It doesn't matter what you do to the intensity of that light. The only thing that you can do here is you can increase the frequency or increase the energy. So what we can do is we can say, well, I was in the green end of the spectrum, let's move to the blue end of the spectrum. Right? Blue end again, shorter wavelength, higher frequency, therefore more energy. So now what I'm going to say is I'm going to shine, that's also a torch, I'm going to shine blue light onto this metal surface. Now blue light, as we've seen here, has that frequency, so we can say therefore the photon energy for blue light, Planck's constant times the frequency, our photon energy for blue light is then 4.42 times 10 to the negative 19 joules. Now what we can see is that things are going to happen. Things are going to happen because the energy of a photon is greater than the work function of this metal, which means that every time an electron gets struck by a photon, it has enough energy to escape. Has enough energy to escape from the surface of that metal. So as soon as this electron jumps off the surface, we say that the photoelectric effect has occurred, or we say that we have a photoelectric emission, or we say that this is a photoelectron. All of those are the same thing. It just means that we have successfully ejected an electron from the surface of a metal. Right. Now we ask ourselves the question, we say, but wait a minute, it only needs 4 times 10 to the 19 joules, and we've given it 4.42 times 10 to the 19 joules. Where does the rest of it go? The rest of it, as with the electrons in here, goes towards kinetic energy. Now, kinetic energy allows us then to use this formula, which says that the energy of a photon is now equal to the work function plus the kinetic energy that is gained by that object, by that electron. So in this case, we're going to say the photon energy, 4.42 times 10 to the negative 19, is equal to the work function, 4 times 10 to the negative 19, plus the kinetic energy. So here you can then solve to see that this electron not only escapes from the surface of the metal, but it gets to leave there with 4.2 times 10 to the negative 20 joules of kinetic energy. Right. It can then go further than this, where we now say, well, that's the kinetic energy. How fast is it actually going? And we use the formula Ek is equal to 1/2 mv squared. This formula is given, where Ek we've just worked out 4.2 times 10 to the negative 20. The mass of an electron is given as 9.11 times 10 to the negative 31 kilograms. And we can then solve for the velocity of this electron as it escapes, and that would then be 303,655 meters per second. Right, so again, your mass of the electron is given And this can only happen because the photon energy has exceeded the work function of this metal. Right? At this point, we can now ask again, we can say, what would happen if we increase the intensity of this blue light? And now, because we are already ejecting electrons, by increasing the intensity, I'm going to be increasing the number of photoelectrons that are ejected. Right? Because I'm already ejecting electrons, if I increase the intensity, I'm going to eject far more electrons. Okay? So the intensity only happens, or the intensity only matters once the photon has more energy than the work function. Right. There is an extra bit of terminology here. We sometimes say, or just it's related to our work function, where we're saying that the work function for a specific metal is going to be, again, Planck's constant multiplied by some specific frequency. That frequency is known as a threshold frequency. It's called the threshold frequency because that is the minimum frequency required to eject an electron. It is the threshold that must be crossed in order to let the photoelectric effect happen or take place. Right? So threshold frequency and work function are pretty much the same thing, except that the work function is an energy and threshold frequency is a frequency. Both of them, though, are specific to a specific type of metal. Right. This can be asked in a number of ways. The first way where this happens quite often is in some kind of electric circuit. So an electric circuit is one in which you have, for example, a light bulb or an ammeter. Both in. And here we have a metal. Right. So as you can see on this circuit over here, in this circuit, no electrons or no current is currently flowing. Right? The reason for that is we have an open circuit. There is no way for the electrons to jump across here. The negative terminal of the battery over here, which means that we are going to have a buildup of electrons on this metal surface. Now, what we can do to prove that the photoelectric effect is happening is we can say, I'm going to start by shining a green light on this surface. Right? And they would normally then say something along the lines of, let's notice that the light bulb doesn't shine and there's no current registered. Explain. Right? And you're going to say, this is happening because the energy of a green photon is less than the work function of whatever this metal is. The next question then is always, okay, well now we're going to increase the intensity of this green light. What do you notice? And obviously your answer is still nothing. Right? If one photon doesn't have enough energy, 10 photons still will not have enough energy. So nothing happens, no current, no light bulb. We then say, okay, let's pick up something like a blue light. Blue light again, shorter wavelength, higher frequency. And what do we notice, or they would often say, it is noticed that when a blue light is shone on this object, the light bulb goes on or it starts to register a current. Okay, explain what is happening, and you're saying, this is the photoelectric effect. Blue light photons have enough energy to overcome the work function, or the frequency of blue light is greater than the threshold frequency for this metal, which inevitably means that each electron absorbs a photon, and when it absorbs a photon, because there's a potential difference between these two parts of the circuit, the electron then heads across to the other side of the circuit. There are two follow-up questions from this. The first one is, what would happen if the frequency of this blue light is increased further, meaning if we now take it to ultraviolet light? And we often are tempted to say, well, if the frequency increases, the electrons are going to have more kinetic energy and therefore they're going to fly across there even faster. It's partly true, but not really enough to matter. So in this case, increasing the frequency has no effect on the current in that circuit. What would have an effect on the current in that circuit is if we increase the intensity of blue light, because by increasing the intensity, you're increasing the number of electrons that are jumping across this gap. Each electron carries a charge of an electron, and by having more electrons jumping across the gap, you've got more charge carriers and therefore a bigger current flowing through the circuit. The other way that we commonly see this is in the form of a graph. There are two common graphs that we come across. The first one is a graph of kinetic energy versus frequency. So this is obviously the kinetic energy of an electron against the frequency of the photon. And then they would give you a graph like this, and that's the diagram over there, and they ask you then a range of questions on it. So what you should hopefully see, let's just put in a value here. What you should hopefully see is that when the frequency is less than 6 times 10 to the 14 hertz, the photon has no kinetic energy. So what this tells us is that anything less than 10 to the 14 hertz, this part over here, means that our photon energy is less than the work function. And then as you can see, once we pass this point, as you increase the frequency, the kinetic energy just continues to increase. So we say E is now greater than the work function, and therefore our EK continues to increase. Which means that this point over here, our x-intercept this is our threshold frequency. What we have here is our threshold frequency, and then what often happens is you are asked, or they draw a dotted line to this point on the graph and label it X or C or something like that. At which point they say, what is this value here? Right? And at this point you're going to use the formula, which says E is equal to our work function plus the kinetic energy. And we're going to say, at the point that our kinetic energy, that our frequency is 0, that means 0 is equal to work function plus EK, and therefore EK is equal to our negative work function, which means that this point on the graph is the negative work function. So over here, because this is the frequency axis, this over here gives us our frequency, this point here gives us our threshold frequency, and then if you extend this graph to find the y-intercept, our y-intercept is going to be our threshold, or our work function. What we should hopefully be able to see at this point is that the gradient of our graph here, where work function is a constant, E is equal to HF, the gradient of this graph is kinetic energy over frequency. Gradient always taken as whatever's on the y-axis divided by what is on the x-axis, and so the gradient of this graph will always give us Planck's constant. And then finally, the last type of graph that is not as common, that also comes up though, is a graph of kinetic energy versus velocity. Sorry, photon energy versus velocity. So here we have on the y-axis our photon energy, and on the x-axis our velocity squared. Now hopefully immediately you should see that velocity squared is obviously very closely related to our kinetic energy. And this graph normally looks something like this, where we are once again either labeled or given that, where we now can say, calculate the, or answer following question. So they say, right, so what this graph over here allows us to do is it allows us to firstly see when the velocity is 0, and we're again going back to this formula, E is equal to our work function plus 1/2 mv squared, which is our kinetic energy. So when the velocity is 0, this energy over here is going to be exactly equal to the work function. So we read off the graph there, we can read the work function. And then a similar question can follow where we're given these two graphs and asked which one of these graphs or which one of these metals is going to eject electrons more easily, and you're going to say because this has a lower work function, electrons will be ejected more easily. The gradient of this graph is, well, not all that much more complicated, except that now we say the gradient of this graph is again, gradient always y-axis over the x-axis, and so the gradient of this graph will always give us, well, technically half the mass of an electron, but we can just say it gives us the mass of an electron. That's it.
All right.